Okay, so this is a set of notes on logistic growth, and this is going to take a while because it's just tedious work. But essentially, logistic growth is a application of solving separable ODEs. So let's take a look here. We're actually going to talk about three types of growth. The first one we're going to hit is exponential growth. Okay, and this is essentially growth that is only dependent upon the current population size. So this is growth where as the current population size gets bigger, right, it grows faster. So you're going to get a curve that goes like this, right? So what we have here is we get a ordinary differential equation, and we say that the change in population, that shouldn't be p, that should be t, right? The change in population with respect to time is equal to some constant times the current population level. Okay, so growth is dependent upon the current, the rate of growth is dependent upon the current population level. Now, lots of things grow exponentially, okay? But this is kind of a model that we use for these situations. All right, so this is a separable ODE. And we're going to find a general solution to it. Okay, so we take 1 over p, right, is equal to k times dt. And we take the integral of that, right? So this gets me the natural log of the absolute value of p is equal to kt plus some c1. Now, I can ignore that absolute value because the population, you can't have like negative of something, right? So that's pretty clearly going to be a positive value. So let's take e of both sides, and that's e to the kt plus c1. I can break that into a product, e to the k times e to the c1. Now, here's an interesting note. This is a constant, this e to the c1. So I can make this p equals some constant times e to the k. Now, that constant is actually a very specific constant. And here's how this works out. Let's say that p sub 0 is the value of p at time 0, right? Then this means that p sub 0 is equal times c times e to the, oh, this should be a kt. There we go, kt. Right, 0 times k, which is just 0, which means that p sub 0 is in fact that constant c. So this means that I can break out my solution to p is the population at time 0 times e to the kt. Okay, so the big idea here, here's the carryaway, is that if I have an example of exponential growth, right, so this is the ordinary differential equation, it can be solved as p times p sub 0 e to the kt. All right, so now this is a shortcut. So this is like something you want to put in your notes and have memorized, right? So like every time you hit exponential growth, you don't have to solve this. You just go straight to there. And this is a shortcut in the problem solving process. All right, so let's look at an example of using an exponential growth problem. Okay, so here we go. Let's say we know that at time 2 minutes, or sorry, on day 2, rather, on day 2, I have a population of 100 fruit flies. And that on day 4, I have a population of 300 fruit flies. And I want to know how many fruit flies did I have at time 0? That's my question, right? Okay, so I know this. The population of day 4 fruit flies is the population of day 2 fruit flies times e to the 2t. Why? Because I just made my initial day 2, right? And if I do this for 2 more days, not 2t, sorry, 2k, right? If I make t 2, that's going to get me to day 4, right? So the question here is just like, what is this constant value k? So 300 should be 100 e to the 2k. E to the 2k comes out as 1/3. No, that's not 1/3. That's 3. There we go. So the natural log of 3 is 2k. K is the natural log of 3 over 2, which I'm going to I'm going to leave it right there. Yep. So now I have the value of k. Okay, so that's usually like something that you have to do. You have to use the data to find that constant. Now, what I know here is the initial value, P0, should be, sorry, that's not true. The value at day 2 should be 100 times the initial value times E, right, times K, so that's the natural log of 3 over 2, times 2 days, right? So this is our basic formula. The 2's cancel. So 100 is the initial value times e to the natural log of 3. Well, that's nice, because 100 is now the initial value times 3. So the initial value is 100 over 3, which is like 33 1/3. Best guess, since I can't have 1/3 of a fruit fly, is that the initial value is approximately 33 fruit flies. So I probably started with 33 of them. 2 days later I had 100. 4 days later I have 300. So they're growing exponentially. Now, if you ask yourself, like if you're in Abe's class, this is probably not exactly true, because like fruit flies actually don't grow exponentially, because in the short run they will. In the short run they will appear to grow exponentially, but eventually they'll hit a carrying capacity, and they'll end up where we're going to talk about later in this set of notes. They'll end up in logistic growth. Okay, so let's look at the second type of growth here. We're going to call logarithmic growth, and in some cases it's also called exponential decay. Okay, so if I have logarithmic growth when increasing, or exponential decay when decreasing, the picture is basically this. I have a current population. It is growing, but it's growing to some limiting factor m. Or I have a current population and it's decreasing to some limiting factor m. Okay, so what we have here is, if it's doing this, it's only going to be dependent upon its distance to that limiting factor. So in both of these cases, the distance to that limiting factor is the absolute value of p minus n, m. So if it's increasing, it's going to make like a curve like that. And if it's decreasing, it's going to make a curve like that. We tend to call this logarithmic growth because it's following a log function. And we tend to call that exponential decay because it's like e to the negative x is what it kind of feels like. All right, so let's see what's going on here. Okay. The model here is that the change in population with respect to t is equal to k times the distance between m and p. Okay? And in reality, that's going to be k times the distance between the absolute value of m and p. Okay? So the question now becomes, like, how do I solve this differential equation? All right, so let's take a look here. So if I take this is again, what you call it, separable, right? So I get dp over m minus p is equal to k times dt, right? I take these integrals, right? So this is going to give me the natural log of m minus p is equal to e to the, or sorry, is equal to kt plus some c, right? We'll call it c1. We play the game before, like we did last time. MP is equal to some constant, right, times e to the kt. Well, that looks familiar, which basically says that I've solved this, but I've solved it for m minus p, right? So the distance from the limiting factor is equal to some constant times e to the kt. So the big idea here is that if I have, let's kind of get a little bit of space here. Delete it. There we go. All right. So if I start with dp dt is equal to either k times m minus p, or dp dt is equal to some constant p minus m. It doesn't matter which one. This is always going to yield the absolute value of m minus p is equal to some constant times e to the kt. Now that constant is not as clear as it was on exponential growth. Okay, you actually have to go hunting for that constant, which makes it a little bit more challenging, right? Because we're going to have to find a couple of things here to get a good equation. So usually when we discuss this, we tend to discuss it actually as exponential decay, because it happens more frequently in nature than kind of logistic or logarithmic growth. That's not logistic, it's logarithmic. So I'm actually going to work an exponential decay problem here. Okay, so the canonical example here is something that's called Newton's law of cooling. And what happens here is you take something out of, let's say, an oven at time 0, right? And there's an ambient temperature of the room. So the thing that's coming out of the oven is higher than the ambient temperature. And you take that thing out of the oven and you put it down on the counter. And what matters here is to the rate of cooling is how close is it to the ambient temperature. And what will happen is you'll get a curve that looks like this, and it'll approach exponentially the ambient temperature over time. So the if you think about this, you take a pan of brownies out of an oven and you sit it on the counter. In the first couple of minutes, that pan of brownies is like cooling really, really, really fast. Okay, so let's build an example of this. Let's say that we have a situation where the ambient temperature is 60 degrees, right? And the current temperature, so the temperature when we take it out of the oven, is 100 degrees. And the temperature at time 10 is dropped 10 degrees. So in 10, let's say, I don't know, 10 minutes, it's dropped 10 degrees. So the question is like, when, right? So when, at what time will I be at 80 degrees? Okay, so this can be modeled as like the change in temperature with respect to time is equal to some constant, right, times P minus 60. And I can do that because like I know that the ambient temperature is below the current temperature, so I know that P minus 60 is positive. So we're all good there. This yields from what we said before that the absolute value of P minus 60, is some constant times e to the kt. This is, again, we know that this is positive, right? Because nothing's going to get colder than the ambient when you take it out of an oven. All right, so let's say this. If I use this piece of data, right, 100 minus 60 should equal C times E to the K times 0, which means that, well, 40 is equal to C. Okay, so I've got that piece, right? I now know that P minus 60 is 40 E to the KT. All right, so I have the C. Well, I can rearrange this a little bit using the second piece of data, right? So 90 minus 60 is 40e to the kt. Gets me 30 is 40e to the kt. 3/4 is e to the kt. And we're going to start some estimating here at some point. Let's see. So the natural log of 3/4 is kt. Oh, wait a minute. T here. This is 10, right? Yeah, because we're at time 10. There we go. So that t is 10. So this should just be 10k. So 1/10, the natural log of 3/4 should equal k. Now, I don't want to carry that thing around. I'm going to make a decimal equivalent here. I'm going to get a whole bunch of decimal places. 0.0287682 is k. All right. So let's see what happens here. Let's clear out some space. We've done all this, right? We'll delete that. And we'll keep going. This means that, what do we got? P minus 60 is like this value. 40 times e to the negative 0.0287682k, right? So I want to know when I'm at 80 degrees. So that's when it's 80 minus 60 equal to 40 times e to the negative 0.0287782k, or 682k. There should be a 6 there. A 6, right? So this is when it's 20 equal to some craziness here. 20 is equal to 40 times e to the negative 0.0287682k. So this is going to be when it's 1/2 equal to e to the negative 0.0287762k. Then the natural log of 1/2 is equal to negative 0.0282682k. Or no, this is not k. Eek, that is k, so this should be t. T. Okay, sorry about that. All right, so we divide both sides by this awful number, and we get t is approximately 24.094. So from time 0 to time about 24 minutes, the panda brownies will cool, or whatever we're cooking is going to cool from 100 degrees to 80 degrees in 20 minutes. So the technique here is you have to find two constants. You have to use the one data point to find the C, and the easiest data point to do that with is the data point from time 0, and then use the other data point to find the K. And once I have the C and the K, I can make a direct relationship between the temperature and the time. So there you go. That's logarithmic growth. All right, so the last piece here is the more complicated one, which is logistic growth. Okay, so logistic growth is the idea that we are combining two factors here. So logistic growth, and this is actually like the more common one that happens in nature, is that growth is actually dependent upon two things. It's dependent upon both the current size of the population and some limiting factor. Now we tend to call that limiting factor the carrying capacity. So if you take apes, you'll hear about that. So this is kind of mathing out some of that. In order to do this, I need to like establish a little bit of a what's it called? A little bit of math here, just to kind of get us to something that's useful. If I take 1 over p and add that to 1 over m minus p, right, I get a common denominator here, so this is going to be m minus p plus p over p times m minus p, right? The two p's cancel out, leaving with me with m over p times m minus p, which leaves me, well, I can be a little bit clever here. I'm going to divide everything through by m. So that's going to take the m out of the top, leaves me with 1. Taking m out of the bottom leaves me with 1 minus p over m. Okay, so that's an idea that I'm going to hold on to for a little bit here because it's kind of relevant to what I'm doing. All right, so this is just like kind of a lemma that we're going to use later on because I don't want to spell all this math out again. So 1 over p plus 1 over m minus p gives me 1 over p times 1 minus p over m. Just hold on to that thinking, okay? It's in the notes. All right, so I don't need that right now to explain logistic growth, but it's about to come up and be relevant. All right. Okay, so we've said that logistic growth is where the population with respect to time is going to be influenced by both the current population and the distance of the population from the carrying capacity. Now, for simplicity's sake, we're going to assume that the carrying capacity is like larger, and we're going to write this as 1 over p, 1 minus p over m. Okay, so what's the logic there, right? You could, there's a kind of a ratio game going on here, but we'll play this out. Usually when we set up logistic problems, this is how they're going to get played out, is this 1 minus p minus m is kind of communicating the idea of like my ratio of my current population to the carrying capacity is approaching 1, okay? So if that kind of makes sense, I want to make the distance from the carrying, the ratio of me, the current population to the carrying capacity, I want that to approach 1, because when the current population and the carrying capacity are equal, that thing is going to be equal to 1. So this actually sets up the correct formulation. What happens here is this is going to produce a curve that is this like S-shaped curve where you have a point of inflection here. It's always increasing. This part of the curve represents exponential growth, okay, because that's where like this P is most dominant. This part of the curve feels like logarithmic growth because that's where this factor is most dominant. And as you go through time, you start finding that the population starts gaining really, really fast and then slows down as it approaches its carrying capacity. Okay, so we have to solve this ordinary differential equation, which is this 1 dp dt is equal to k times p times 1 minus p over m. Okay, so this is separable. So this is going to give me 1 over p times 1 minus p over m dp is equal to k dt, which we can take the integral of both sides. But see, we did this work before as I started this section where I said, oh, this is the same as 1 over p plus 1 over m minus p dp, which gives me now this is just going to be kt plus c, right? All right, so there's a little kind of small sleight of hand that goes on here. All right, and what we're going to do is we're going to change this to 1 over p minus 1 over p minus m dp, because that's going to facilitate some calculations in a minute here. If I do that, this works out to be the natural log of the absolute value of p minus the natural log of the absolute value of p minus m is equal to kt plus, let's make these c1s, right? So this is going to give me the natural log of the absolute value of p over p minus m, right? Oops, sorry. That's the glitch. There it is. I'm going to change the ordering here. I'm going to say that the natural log of p minus m minus the natural log of p is equal to negative kt minus c1. Aha, there we go. So that makes this now the natural log of p minus m over p is equal to negative kt minus c1. All right, so there's some little mathematical trickery going on there, but so far we have not broken any rules, and we're going to get to a good formulaic solution here. All right, so looking at that, I can take e of both sides, right? So this is going to give me the absolute value of p minus m over p is equal to e to the negative kt, right? And what we can do is the same trick we've played before, is put a constant in front of that, right? All right, so a little more sleight of hand here. We know that the carrying capacity is larger than the population, so this is actually m minus p over p is c times e to the negative kt, which means that m over p minus 1 is c times e to the negative kt, and m over p is equal to c e to the negative kt plus 1. All right, so there we go. A little bit of cross multiplication, and I get that p is equal to m over c times e to the negative kt plus 1, right? So what's the takeaway here? Okay, so the big idea that we're going to have in this is that if I start with logistic growth, right? So I start with dp dt being k times p times 1 minus p over the carrying capacity, then this solves as p equals the carrying capacity over c times e to the negative kt plus 1. Okay, so how the heck do you use this thing, right? So let's take a look at that. All right, so let's say we're on a reservation, and at time 0, there are 40 elk in this reservation. And that at 5 years later, there are 104 elk on this reservation, and we assume that the carrying capacity of the reservation is 4,000 elk. So lots of elk, right? So the question is just like, where's the population going to be after 15 years? All right, so this thing models as, we're going to assume logistic growth here is some constant times p times 1 minus p over 4,000, right? Now we know from what we just did that p should equal 4,000 over 1 plus c times e to the negative kt, right? So that's pretty straightforward. At time 0, we have 40 elk, so that means 4,000 over 1 plus c times e to the 0, which means 40, plus 40c should equal 4,000, which means 40c is equal to 3,960, which means c is 99. So we got a nice constant there for c. All right. So let's look at where we go from here. I want p of 15, right? So I know that at time 5, I have 104 elk, right? And that should equal 4,000 over 1 plus 99 times e to the negative kt. Or, t here is time 5, right? All right, so there we go. So I know 104 times 1 plus 99 times e to the negative 5k is equal to 4,000. This means 1 plus 99 times e to the negative 5k is approximately 38.46153, which means 99 times e to the negative 5k is approximately 37.46153. If I divide by 99, e to the negative 5k is approximately 0.378399. We take the natural log of both sides, which means negative 5k is approximately negative 0.971805, which means that k is approximately 0.1943610. I'm going to divide both sides by 5. So, all right, I have the c, I have the k. This means that the population can be modeled as 4,000, the carrying capacity, over 1 plus 99 e to the negative 0.194t. And if you happen to put 15 in there for the t, you're going to get approximately 628.538. So about 628 elk at the beginning of the 15th year, after 15 years, right? So it'll be the end of the 15th year, right? So there you go. We've just used this to estimate a population. All right, so the last thing is like, what about that point of inflection? Because that seems like an important thing in this logistic curve. So we now have a bit of a model here, right? So it's like, so the logistic curve is this. It's like, where does that point of inflection? Where do I stop increasing faster and start increasing slower? Well, the nice thing about this is that the point of inflection always occurs when the population is at half its carrying capacity. This is halfway between 0 and m. Okay? So, in our example here, that means the population's at 2,000 because the carrying capacity is 4,000. And we know that this is like 1 plus 99 e to this negative 1.194 t, right? So we back that around, right? 2,000 plus 198,000 times e to the negative 0.194 t is equal to 4,000, right? So 198,000 e to the negative 0.194 t is 2,000. Oh, that's nice, right? E to the negative 0.194 t is 0.01. We get, what do we got going on here? We take the logarithm, right? So this is negative 0.194 t is going to be about negative 4.595, which means that t is about negative, or is 23.686. So if this is time, if we, this t is from time 0 moving forward, in our model from when we had the beginning of our experiment, which was when the elk population was 40, right? The elk population will grow to 2,000 in approximately 23 and a half years, which means we're going to get an idea of where that point of inflection is, which means we'll probably be about 40 from the carrying capacity and about 46, 47 years. All right. To find that, remember that there's a limiting thing going on there, but a good estimation would be to say around 46, 47 years we're going to get close to the carrying capacity for these animals. All right, so that was a long video. The good news is it's the last topic in this entire course. And we'll deal with some growth problems in class.